So good morning. If you want to say a personal prayer, if you want to say in Our Father, Hail Mary, Glory be, one of our set
We
prayers,
do a Hail Mary.
that is absolutely fine.
Hail Mary. Wait, name Father, Son,
Wait,
Holy Spirit.
yep, there we go. Everybody
Hail
ready?
Mary,
Father,
full of grace. The Lord is with thee. Blessed
blessed
thou amongst women, blessed is the fruit of thy womb. Holy Mary, Mother of God, pray for us sinners now at the hour of death. Amen. In the Father, Son, Holy
all
Spirit.
right. Thank you. Thank you. Thank you. All right, gentlemen. So I hope we have a great day. So happy April 1st. And along with our prayer, let me read you our short mustard seed for today. It says, when I say everything is going to be all right, I don't mean that everything is going to be the way you want it to be. So that's a great one for us to hear today. Everything is going to be all right. It may not be the way we want it to be. Like this, I definitely would prefer that I had you guys at school right now, but it's going to work out just fine. All right, so let's get started for today. Yesterday, okay, I'm going to switch to my pinned video, make sure you can see the screen. Okay, first of all, what I'm going to try to do all the time is put your homework up here. So you'll see we're going to work on that today a little bit. So hopefully we'll have time at the end of the class, but I'll get you started on that. So the one good news of yesterday was that Blackbaud came back up and is now operating. So I'm excited about that. So now you can pick up your course documents and everything.
Wait, do we have to print that off?
You do not have to print that off. So I want you to, so that's a good question. Any documents that I put online that are on the course documents, just know that I know some of you, I mean, I myself am running out of ink on my printer. I don't necessarily want to go out and get any. So if your printers are not working and you don't have the ink or anything, you can always do it on notebook paper by hand. All that I ask is you follow my same format so that I can see that. Any documents I'm now sending you, I'm going to try to Google Forms or send it to you in Word. So you can also type on your computer and just send me that document back. So that works just as well. So don't stress too much about printing it off. It's probably, it helps. I know I like to have it printed to write on. So you do not have to though. So it's not required that you print it and you hand write on to that. You can even type in another Word document your answer to the question. You don't have to write the questions back. Okay? So, any other questions before we get started? Okay, for the sake, let's see, not the screen share. I'm going to go ahead and mute you all, again, just for the sake of management of the class. And again, if you have questions, you can either do the raising of the hand signal or unmute yourself and then ask the question. All right, so we'll go back in this direction. All right, so yesterday we ended with, just to clarify some things. So in the example that I gave yesterday, I said that there's an action and reaction force, and I wrote down that the force was 100 newtons. I just made up that number just for the sake of the example. But where we left off yesterday was changing Newton's second law from looking like this, where we had force net equals mass times acceleration. We replaced acceleration with the definition of acceleration, and we said mass is change in velocity, acceleration is change in velocity over change in time. So this is where we ended yesterday's class. So here's where I'm going to begin. So if you are writing down these notes, which I recommend, we'll go ahead and start where we left off yesterday. So we had the net force is equal to mass times change in velocity over change in time. We multiplied both sides by our change in time. So then we looked at the equation like this. Force net times change in time is equal to mass times change in velocity. I guess I don't know if I necessarily write that in there. Okay, mass times change in velocity. Our velocity is a vector quantity. The force is a vector quantity. What this equation allows us to do, instead of looking at Newton's law like this puts the factor of time in there. So what we did know is, of course, I need a force to change an object's motion. So the question we want to answer today is, what effect does how long I apply that force have on how I change an object's velocity to make it move in a different way? So if I apply a force over a short time, what effect does that have on its motion? And if I apply force over a long time, what effect does that have on its motion? Okay. So for the sake of notes, we're going to define some of these. So if you read in your chapter 6, the homework that was due today, there's a definition for each side of these things. This side we call an impulse, and this side is momentum. All right, so let's define each one of those. Momentum. Okay, we're going to give that the lowercase p. It is a vector quantity. And so a couple things. It's a vector quantity. Its units are kilogram meter per second, the same as mass times a velocity. Saying that it's a vector quantity means it has both magnitude and direction. And the equation to find momentum, well, actually, first I'm going to say directly related to mass and velocity. What I mean by that, directly related, just like we had force and acceleration were directly related. If I increase my mass, I will increase my momentum. If I increase my velocity, I will increase my momentum. The equation to find momentum is equal to mass times velocity. So we kind of take out this change, and we'll come back and describe why that change is in there. But if I just want to know an object's momentum, momentum is mass times velocity. Its direction depends on the direction of velocity. So momentum is a vector quantity. It has direction. Its direction is going to be the same as our velocity's direction. If I double my mass, I will double my momentum. If I double my velocity, I will double my momentum. So I know you guys have used this word before. You often say, oh, it has a lot of momentum. It didn't stop because of its momentum. I know you have used the word before, but now we're going to put it into a mathematical equation. Okay, I'm going to unmute you all just to pause and say, anybody have any questions? Everybody good? Thumbs up? Are we good on our notes? Because I only have so much space. I want to keep this part up over here. Are we good to erase that? All right, we'll do an example calculation of what we are looking at here. So I'll go ahead and mute you all again. Okay. Okay, good. So that's our momentum. So let's say, for example, okay, what is Wes's momentum? Okay, when he runs with a velocity of, let's say, how fast are you, Wes? 10 meters per second. Going west, okay? Now I'm just guessing the average mass of a person is 75 kilograms. All right, so Wes, if you have a mass of 75 kilograms and you run with a speed of 10 meters per second in the direction of west, so 10 meters per second west would be your velocity. What is your momentum?
Would it be?
So I'm going to just pause. All right, David, what's our first step in problem solving? Go ahead and I'll unmute you.
Is to draw a picture.
Draw a quick picture. Now, this is our first problem, so it's going to be very, very easy. All right, however you want to draw Wes. There you are, Wes. Should I put the hoodie on you? That makes it look like you have long hair. We'll make that all jersey. Wes is running on the football field. He's got the ball in his hand, and he's going to be running with a speed of 10 meters per second. I guess if he's going west, he should be going the other direction. I'm going to cross that out and just say east, so it matches my picture. The only reason I really wanted to put that in there is to emphasize that momentum has direction. Okay, so that's basically it. His mass is 75 kilograms. So his momentum, our next step, list what we know, right? Draw a quick picture, list what we know. What's the equation that we want to use? Mass times velocity. So very, very easy. 75 kilograms times 10 meters per second east. So we're going to put our direction there. Okay, so remember, we can choose our direction positive and left as negative. So instead of me putting the word east there, because I don't know how to multiply, divide, subtract east, but I can do that with our positives and negatives. So just as we had with motion, we're going to assign direction to our velocities. The same direction is also applied with momentum. So I can take away the word east, that is not needed, and keep that as a positive value, and that gives me my momentum. So obviously, easy math. TJ, what's 75 times 10?
750.
Very good. 750. Okay. What? So a number by itself is meaningless. What do I need to go with that?
kg meters squared.
Very good. Kg, kilograms, meters per second. It came out to be a positive value, so I'd go back to my picture to say it's moving in the positive direction, and that's my momentum. All right. Thumbs up. We are good. Give you a minute to okay, what I really had over there, looking for my, there we are. Okay, if we go back over to here, what I really have over here is this change in velocity. So we would assume that Wes started from rest and he changed his velocity. So But if he is moving with this velocity constant, this would be his momentum under that velocity. Okay, let's go back and talk about what does this change mean. Okay, so that's going to become important when we want to talk about the left-hand side. So, everybody good if I get rid of this? All right. Okay, so now what does it mean to have a change in momentum? Okay, the only way you're going to change momentum, it occurs if you change velocity or mass. Okay, obviously, if momentum depends on velocity and mass, your change in momentum would depend on both of those. Typically, if you're talking of one object, it's not going to change its mass. But in a collision or something falls on me, those two things together become one mass. But for the most part, we're going to keep mass constant. So if I have a change in momentum, that's going to be a mass times a change in velocity. Okay, so change in momentum is mass times change in velocity. We're going to use this equation if I'm changing my momentum due to a change in velocity. Okay, and Jack Miller. In mathematically, how do I determine a change in something? Do you remember that?
How do you determine a change in something?
Right, so that's kind of a tough question. When we had change in velocity, what did that really mean? What would I put over here? How would I determine the change in velocity?
Like starting, ending, like
Good, yes.
0 to 100 or something.
Zero,
Like,
that's correct. Except when we did the change, it wasn't starting to ending, it was,
It's already moving.
well, it was the final minus the initial. So we ended up with what we ended with minus what we started with. So I'm going to erase that. So add to your notes after this. Delta means change in, and it always means final value minus initial value. Okay. So that we're recalling from way back when we did all that. All right, Joseph, you have a question?
Yeah, do we always keep the what do we always keep constant?
Okay,
Like,
that's a good question. Typically, we're going to keep mass constant. So it's going to be the same object. So like, okay, so the scenario would be we use Wes, right? I'm going to continue using you as an example. If Wes is running on the football field, right, his mass isn't going to change. So he can run, and let's say he was going 10 meters per second, and then he's going to get faster, which is going to be our example that we're going to do. How much did he change his momentum? Where somebody comes to tackle him and they actually literally jump on him, right? Their legs are no longer moving. They actually became like a backpack on his back. In that case, his mass would have changed, and therefore that would have changed his momentum because he's trying to run with more mass on him. Does that answer your question?
Mm-hmm.
Okay. All right. So does anybody else have any other questions? All right. Very good. This is working well. All right. So let's put some numbers to that. Let's say Wes went from 10 meters per second to 20 meters per second. He doubled his speed. What is his change in momentum? Okay, so if he got faster, how much does he change his momentum? What is Wes's change? You know, who's my English people? Wes, if I want to make a possessive, do I want to put apostrophe S or just the apostrophe? What is Wes's?
You can do both, can't you?
Apostrophe.
I like apostrophe S.
Oh.
I think I'm going to go with that. What is Wes's change in momentum if he goes from 10 meters per second to 20 meters per second? Okay. So going from the same problem that we just did, so in this case, our picture, so drawing a quick picture, I'm going to assume 10 meters per second to 20 meters per second east. So in this case, he's going to be going both directions, east. So that's going to be important because I could go and turn around and go the other direction, which will do some problems with that. If I'm going 10 meters per second east to 20 meters per second east, so first of all, in my picture, I'm going to take east to be positive, west would be negative. He starts right here running, right? Going 10 meters per second. Sometime over here, he's going even faster. Doesn't matter what he did in between. Over here, he is going double that speed. So I'm actually going to make that vector twice the length, right? He's going twice as fast. 20 meters per second. He still has the same mass, which is 75 kilograms.
So why wouldn't it add on to the momentum if they're going in the same direction?
Well, we could do this in two different ways. We can find this momentum and then find that momentum and take the difference between the two, how much he changed. Or we can just take the difference in their velocities multiplied by mass. So if we go back to, so I'm not sure that answered your question, Joseph.
Okay.
Why? Well,
Well,
that answer?
wouldn't 10 meters per second just be added on to 20 if that's his
Oh, and say that
acceleration
his
of it?
momentum is his mass times 30?
Yeah.
No, because he does not have a velocity of 30 meters per second.
Okay.
So what we want to know is how much did he change his momentum? Okay. So in the end, he's going to have a certain momentum here. It should be twice as much as what he had over here, which since it was 750, we'd have 1,500 kilogram meters per second over here. However, the equation to solve for your change, so the question was, what is your change in momentum, right? So that's our question. The equation to find that is that change in momentum is equal to mass times change in velocity. So that's going to be mass times your final velocity minus your initial velocity. So in your notes, I'd said, remember that final and initial, the change means final minus initial. So that's how we're going to write this equation here. So we plug in his mass, 75 kilograms. His final velocity is positive 20. His initial velocity is 10. Right? So what we will find is he changed his momentum by the 775. 20 minus 10 is going to be 10, right? His change is actually going to be the same because it's going to be 10 times 75. So his change in momentum is 750 kilograms per meter, kilogram meters per second. And it comes out positive, okay? Now, we came up with the same number we had before. So what I want to show you is, if I just plug this into my mass times my velocity, I would have 750, right? Kilograms meter per second, not squared, sorry. I always want to write that. That's what comes off my head because of Newton's. That's his momentum here. His momentum over here would be 75 times 20, mass times velocity, which I said is 1,500 kilogram meters per second. So the change is what is the difference between here and here. That's where this comes in. So Joseph, we would not say that I would have a velocity here of 30, but rather that I changed by a velocity of 10, making my change in momentum 750. So if I started with 750, I'm going to have 750 more to get 1,500 at the end. I'm going to pause and let you all write that down. I kind of talk while we are writing. All right, thumbs up. Any questions? Daniel.
So is the answer still 750?
Correct.
Okay.
Okay, let me explain again why. If so I know so often you're writing and I'm talking, and so it's hard to listen while we're writing. So let's go back and do this scenario. So again, Wes is running, right? Here he goes. So he is moving with a velocity of 10 meters per second. He wants to get up to 20 meters per second. How much is he going to have to change his momentum? Okay, so if he changes his momentum, okay, his original momentum would be 75 times 10, 750. That was the first calculation that we had done. If I just asked you how much momentum does he have if he's going 20 meters per second, you would have done the same thing. 75 times 20 would have given you 1,500 meters per second, right? So my change in momentum is, what do I have at the end minus what do I have at the beginning? So the difference between these, because I doubled my speed, I doubled my momentum, but my change is that I only increased by the same amount, right? So if it's like, how do I go from 1 to 2? I have to add 1. I have to add the same amount that I am. How do I go from 2 to 4? I add 2 more, right? So I added the same amount because I doubled my speed, so I doubled my momentum. All right. The reason I wanted to talk about that is, on this right side, that's momentum. So we can talk about just momentum as mass times velocity, and we can talk about the change in momentum, how much momentum is changing, which is mass times the change in velocity. But the question then becomes, how do I do that? How did Wes make himself increase his momentum? All right, so let's go back to this. Okay. Okay, so the left side of the equation is what we want to talk about next. On the right side, we have mass times change in momentum. On the left side, let's talk about how do we do that? Okay. how do you change an object's momentum? Okay. Which is what we've been studying, what we have been studying the whole time. I'm going to have to cause a change in velocity, which means I cause an acceleration, which means I apply a force, right? But this equation says that I can apply that a force over a certain amount of time. So the answer to that question is you can change velocity or mass, right? Mass, obviously, I just have to add more stuff. To change its velocity, you cause an acceleration by applying a force, right? That's what we've known up to this point. But now I'm saying I'm going to apply that force over time, okay? So to change velocity, you can cause an acceleration by applying a force through a time period. Okay. So that's the left-hand side of this equation. This quantity that we're talking about, force times delta T, has a name called impulse. And it is an impulse. An impulse causes a change in momentum. So you have a couple choices here. You can apply a force over a long time. You can apply a force over a short time. But if I want to cause the same change in momentum, I need, one or the other. I can increase my force or I can increase my time. So in our previous equation, what we would say is, okay, if we want to change Wes's momentum by 750 kilogram meters per second, we will need to apply an impulse. So on the left side, we want force times delta T equal to be 750 kilogram meter per second. That force is going to be in the same direction as that change in momentum. So to make the math easy, let's say I apply a force of 10 newtons. Wes, since we're talking about you this whole time, what do I have to apply 10 by to get 750?
75.
75, good. Okay, now I know we're using kind of the same numbers, I'm just doing that for the math, but now what I'm saying is Wes could apply a force for 75 seconds That's a long time to apply a force. And maybe it's the scenario of running is not as good right now. Let's say it's like your car moving. You want to go from 10 to 20 meters per second. You can apply a force, press the accelerator down a little bit for a long time period of 75 seconds, right? That gives us 750 kilogram meters per second. That's how much we changed our momentum. What if I can apply, somebody give me two other numbers that give us 750. I've already called on Daniel. Let's see, Walter, you with us? Give me another number for force. Greater than 10, I want to increase it. What happens if my force becomes, how about I give it to you? We'll switch these. What if my force is 75 newtons? How much time do I have to apply that force?
Oh, wouldn't it be 10?
It'll be 10.
Yeah.
10 seconds. So look at what I did here. I'll pause while you guys all write that down and then we'll talk about it. Okay, in order to change an object's momentum, whatever the object you want it to be, whether it's Wes running, me throwing a ball, right? I can throw a ball, so we'll get back to our baseballs and throw a ball at 10 meters per second and get it all the way up to 20. If I want to change its speed, I can do one of two things. I can apply a force of 10 over 75 seconds and go from 10 to 20 meters per second, if a mass of 75 kilograms, or I can apply a force of 75 over a short time period of 10 seconds to get 750 newtons. So what we're saying here is to cause the same change in momentum, I can apply a small force over a long time or a large force over a short time. Sometimes you want one over the other. All right, so I'm going to go back here and get all your faces in there. All right, I know you don't have it completely, but as we utilize this, it'll start to make more sense. Anybody need more time on writing these notes? Am I good to erase these? Okay. So in that scenario, we could apply a little force over a big time, right, to get the same change in momentum. These are still your vector quantities. Or I can apply a big force over a little time to get the same change in momentum. And why might you want one over the other? So let's get back to our sports, right? So yesterday I used the scenario for hitting a baseball, I believe. So here's our baseball, right? I'm only so strong. So I can only throw it with my force by so much. But the way that I can make the ball go faster and increase its momentum more is to apply that force through a long time period, right? That's called that follow through. So in all sports, whether you're swinging a bat, throwing a ball, kicking a ball, hitting a ball, the longer your hand is in contact, or your club head or your bat is in contact with whatever you're trying to change its momentum, you don't have to apply as much force because you're relying on the time factor. Okay? Sometimes, if you want a large force, you want it to be over a quick time. So that's like, maybe I want to crack something, I want to break something. So if in a collision, if it happens very quickly, there's going to be a large force involved in there, right? So here's another scenario. Guess what this is? A water balloon, all right? So what you'll see on your homework for tonight is I'm giving you extra credit if you go outside and have a water balloon toss, and you might not have a water balloon, or an egg toss, raw egg toss. All right, so if I want to win the water balloon contest, I got to catch this, right? Which means it's going to be coming in at a certain velocity, and then I got to stop it. My two options in stopping it is I'm going to change its momentum from having something to nothing. I have an option of applying a small force over a long time or a large force over a short time, right? Josh Davis, what do you think is going to win you the water balloon contest? Which one of these scenarios? Let's see, I'll unmute you.
But would it be the first one?
I want a small force over a long time. So what's the key in catching it?
Like
Do I
stopping
want to
it.
run in and catch it quickly? I want to go with it, right? So when this is coming in and I want to catch it, I want to go with it. And that's a soft catch, right? So those of you guys that play baseball, when that ball hits your glove, and if you like run into it, it stings. But if you go with it, then it feels much better, right? So to win the toss, you must go with it. All right, so gentlemen, I think we are out of time. Your homework is go on the course documents. There's 2 sheets there. You're only doing the conceptual sheet, not the questions, not the change of momentum. You're only doing the conceptual sheet. Okay, try that as best as you can.
When is it due?
It's not due till Monday.
Okay.
Wait, today's Wednesday? Yeah, I don't see you again until Monday.
Okay.
Okay, so here's my next question for you guys. I got 30 seconds. Who's juggling? Any out there? Beth Miller, have you been practicing? Now listen, this is serious. This is a grade. You have to, now it's not easy, as I showed you. So hopefully you're learning how to see what I'm doing there. I'm putting that ball in my left hand. All right, so hopefully you're getting out there and practicing your juggling. You have till next Friday as a class, and this is how this is going to work for winners of the boot camp. You're going to show me a video, and in that video I'll time how long you've been able to juggle, and I will add your entire class's time divided by the number of students that are in your class, and whichever one of my classes has the highest one, they get the extra credit on it. They're considered the winners. Everybody must do it. You'll be graded just on the fact that you did it. I want, that you tried it. All right. But to be the winners, let's see if I can do it. There we go. All right. You got to get out there and juggle. David, did you watch my video about juggling?
I don't believe so.
All right. Well, it has everything to do with momentum, projectile motion. Get on the YouTube channel and watch it. I give you directions on how you're going to try it. So that was last week's Boot Camp Friday. Wes, question?
Where's the worksheet?
Say that again.
Where's the worksheet?
It should be if you go into Blackbaud. All right, let me share my screen with you real quick. All right. If you go into, let me, hold on here, I don't want that. I gotta get to my Blackbaud tab right here. So if you go into your class documents, your view probably looks completely different. But if you go into your class documents, you should be able to see them all right there. You are only doing the conceptual questions. So I put them in a PDF version and a Word version. So you can fill out the Word version right online. You can change it into a Google document, send it to me, email it back to me. There is, actually, you don't have to do any of that because this one I'm not collecting. I just want you to have it ready for Monday. Probably what I'll do on Monday is just simply have you hold it up to your screen when you log into class and show me that you have it done. Or you can share your screen with me and show me that you have it done. I'm not collecting this one. It's just to make you kind of be accountable to the questions that we worked on today.
What's it called again?
Say that again.
What's it called? The worksheet?
Conceptual questions in momentum. And they come right from your book. I think it's at the end of chapter 6, numbers 1 through 10. Okay, for everybody else, if you don't have any questions, you may go on to your next class. Have a great weekend. I don't see you until Monday. Bye. Thanks for your attention today.
Excuse me.
Yes, TJ.
So for the water balloons, is that extra credit if you?
It is extra credit.
So what do you what do you have to do in it besides like obviously catching it? Like you have to go a certain amount.
Well, it's. Did you go outside? Yeah, just show me how far you went. We'll see who went the furthest. So,
And
just to
so
get you
if you do
outside.
it, is there extra credit if you do it, or is it on who does it the longest?